Hello and welcome to this short podcast on the science of the Doppler effect with respect to electromagnetic radiation. It's going to be very outcome focused because I'm not going to go into very much background of this. I'll just very briefly do that and then briefly look at the equation and spend a little time on some of the applications. And then in a separate video I will do a couple of past paper IB questions that look at this topic. So this is the end for wave phenomena. This is the very last part of this topic, the last section and the last subsection therein. So basically the understanding says Doppler effect for sound waves and light waves, although technically what we're describing here works for any wave where the speed of the wave is vastly different to the speed of anything moving, the sort of source of the observer. Something has to be moving, but the difference has to be very, very large. There's one application that will make use of that, but it's not, strictly speaking, light. But the IB still says in the applications, which isn't actually listed here, but in the applications they do say that you need to do it. Okay, so here is the thing. Sticking with light, the speed of light is constant for all observers and is really fast as well. It's 3 times 10 to the 8 meters per second, and that has an effect. Basically, the previous equations where you had to worry about the moving source, the moving observer, and you had to plug them in, they don't apply anymore. We don't use those equations. It's actually simpler. It's just this equation. Notice that this equation has an equal sign, and then it has a more or less equal sign. And so delta F is the change in frequency due to the Doppler effect. F is the frequency of the source of the wave. Delta lambda is the change in wavelength as perceived by the observer compared to lambda. So delta lambda is not the new wavelength or the new frequency, but it's the change in, be it smaller or larger, because that will depend on whether the source of the waves is coming towards the observer or moving away. V is the relative speed of the source and the observer, and C is the speed of light in a vacuum. Rearranging those equations, I think this is maybe slightly more useful. It tells you that the change in frequency between the source, what is emitted by the source, and what is perceived by the observer is equal to the original source multiplied by the fraction of the speed of light that the source and the observer are their relative velocity. And same applies to the wavelength. Okay, when it comes to the questions, we'll look at some of the putting this into practice. But it's worthwhile looking at a couple of the applications of the Doppler effect. And we didn't really do this in the video for sound because there aren't many applications when it comes to sound. There's some questions, and it's used to explain the phenomena. And I've had one of my students once used sound waves emitted by I think it was an iPhone he was going around in a circle as a simulation of the light effect. But most of the actual real world applications are to do with the EM radiation aspect, and one of those is in astronomy, and this slide here. Let me get rid of myself briefly so you can just see the whole thing. This slide here illustrates part of that. That when if a star is moving towards us, then that light from it will appear slightly bluer than it does if it's moving away from us, when it will appear redder. And if it's not moving towards us or away from us, or if it's moving transversely compared, then its light is the same frequency as emitted by the source as perceived by us. Now, of course, when it comes to stars, if we're looking at stars, we're often looking at the spectra of a star. The spectra of a star has those spectral lines, those absorption lines, and we know by looking in a lab where those absorption lines should be, what the wavelength of those should be. And so it's actually quite easy to compare what we observe looking at the spectrum of a star compared to what we would expect to see using a sort of lab references. And therefore, it's using modern equipment, it's relatively easy to get a good measurement on whether that star is moving towards us or away from us, which is good information to have if you're trying to find out about a star. Let me put me back again. This applies to stars. It also applies to other stellar objects, including large galaxies. Now, this is something that if you do the astrophysics topic option, if that's still an option for you, then you will be talking about this. This is something, or was the clue to something called the Hubble observations of a recessional velocity of galaxies. This picture on the left-hand side shows some, it says nebula, cluster nebula. These are actually from Hubble's original, I think, 1920s observations, when the word galaxy wasn't, believe it or not, I mean, I'm talking almost exactly 100 years ago, wasn't exactly used as we would now use it. So these are actually what we would call galaxies, and they're in different constellations. That's not important. What you can see is that they're kind of smaller and fainter, and that corresponds to these different distances. And at these different distances, here are some images of the spectra. And on the top one, on the closest one, on the Virgo galaxy, you can see these two lines here known as the H and K lines, which are where you would expect them to be in a lab, more or less, very slightly sort of shifted towards the red end of the spectrum. But as the galaxies get further away, you can see these lines shifted to much more into the red end of the spectrum. And the fact that their redshift is greater implies that they are moving with greater velocities away, and this graph plots it. And as a consequence of this, this was the whole concept that the universe is expanding. It's the observational evidence for the expansion of the universe. Rather close to home, another application is use of radar. So radar is a technology which sends out pulses of electromagnetic radiation, commonly radio waves, and those radio waves reflect from an object and go back to the observer, and using specialist timing equipment, then it can measure the normally short amount of times between emission and reflection, and observing the reflected wave can measure the distance to the object. But if you include the Doppler effect there, then you can actually get more information, because as well as knowing the distance, you can also find the velocity. And in the case of a sort of police radar gun here, it's the velocity that they actually care about. So you can the machine will compare the frequencies of the emitted radio waves, which it knows about, and then it measures the frequency of the reflected wave, and will know whether the object is moving towards or away from the radar gun, and with what velocity. The same technology is used in radar pictures in a couple of situations. Here we have a situation showing the output of a weather radar. So weather radar uses radar to detect clouds or precipitation, rain in clouds. And in here you can see on this picture, this is the radar in Billings in the United States. There's a radar station basically in the town there. On the right hand side you can see scale. So green, dark green is approaching -5 knots. RF KTS is a unit of velocity beloved of aviation and meteorology. 1 knot is 1 nautical mile per hour. Sorry. And here the red is moving with a velocity of 5 knots. So -5 means towards and 5 means away. And you can see that on the left hand side of the image it's moving in one direction, on the right hand side it's the other. And so using weather radar you can measure the using Doppler radar you can not just say that the rain is there, you can also measure the relative velocity of the rain and therefore the wind speeds and things like that. Same technology is used in air search radar. So if you have a radar which is there to detect aeroplanes, then again you can not just tell whether the airplane is or is not and what its distance is, but also by measuring the comparing the frequency of emitted and received waves, you can tell the relative velocity of the aircraft. And this can be very useful if you're actually, it is an airborne emitter, because if your radar is in an airplane sending out waves and then reflecting them back, the problem there, particularly if you're higher up than the airplane that you're looking for, is you've got things like the ground get in the way, so it can be very difficult to perceive the object you're looking for against the background. And what a good Doppler radar can do, well, the ground is moving relative to you, but you know how fast you're moving. You can put that into the equation, and so you can take away the ground reflection returns, because they will appear to be being reflected back with the same velocity as you are flying with. Anything that has a different velocity to you, therefore, or is actually moving with respect to the ground, which if an airplane is moving towards you or away from you, it will be, or even a ground vehicle moving away from you, then your radar can pick that up and highlight it. Very useful. The final application that you might come across is in ultrasound. So I said that although with everything we've said as being in relation to electromagnetic radiation, ultrasound is actually sound waves, but it's a very similar process. This is used to measure flows of fluids, generally blood, within a body by sending out sound waves and looking at the echoes, looking at sound coming back. The equation for EM radiation is applicable here, because sound waves through solids and through liquids travel at thousands of meters per second, and the blood flows itself is in the order of centimeters per second. So there's such a big difference in those velocities. Here you can see actually, and again, a scale, red and blue being the false colours applied to this image, with a maximum of 21.3 centimeters per second. So you can use it to measure blood flows throughout a section of the body. Very useful medical purpose. Okay, so I think that's gone through. Say it's just that simple equation there in the bottom right, and we'll look through some some questions involving that in a minute in the next video, and the applications that I have discussed. Thank you very much for your attention.